In this video, I want to take a look at three examples of Picard's method and using them to not so much solve a differential equation, but generate a sequence of approximations to a solution. And maybe if we can see what the limit is, then maybe we get a solution, but maybe not. Anyway, let's start with this one right here. Y prime equals 1 plus y. Of course, initial condition, y of 0 is 0. I should point out this is both a separable differential equation and a first order linear, so you can solve it. In fact, I specifically choose this so that we can solve it and we can compare our estimates with the actual and see that they are in fact converging to the solution. So here we go. The process always starts in the same place. You start with the guess of y is equal to 0, and then you plug it in to here and integrate that with respect to t, well, with respect to, right? So I plug it in there. I got 1 plus 0 ds, the integral from 0 to t, and that is just s evaluated between 0 and t, which becomes a t. I want to point out here, let's take a look at this graph right here. So here's the slope field. Notice that my solution does in fact pass through 0, 0. And it looks like at that point I'm lined up with the slope field. It has slope 1 right there. But you can see that very quickly I'm not lined up with the slope field, so this is not a correct solution. It happens to be good right here. It's got the right, it goes through the right point and it goes through with the correct slope. So it's kind of like it's a linear approximation of the solution. Okay. So then we take that and we use that for y and plug it back in. So instead of 1 plus y, I've got 1 plus t, but I'm using s instead of t because I'm doing the integral from 0 to t. So you integrate that, you get s plus s squared over 2, evaluated between 0 and t, getting t plus t squared over 2. And now we got a quadratic, which looks like this. So what I see here is it's still going through with slope 1. This looks a little bit better to start with, but then clearly it's not right there, and definitely not right out there. But this looks pretty good through here. That looks like it's still hitting that spot really nicely. Maybe not by the time you get up here, but it's certainly it's got a much better feel to it, that it's definitely following the direction, the slope field here, but not over on that side. Okay, so next. So now I take that and I plug it in. So I got 1 plus y, but y is now t plus t squared over 2. So I got to integrate that whole thing. Evaluate between 0 and t. This 3 factorial is just 3 times 2 times 1. Anyway, plug the t in, plug the 0 in, subtract. I get this function now. Perhaps you can see a pattern. T plus t squared over 2, t plus t squared over 2, plus t cubed over 3 factorial, and so on. This one now definitely looks good on that side. Clear up to here, I think it looks really good. Up to here, I'm pointing off the top of the screen. Let me pull the window down a little bit. What just happened? Yeah, so it looks pretty good up there. This bends pretty well to start with, but then it peters off. It looks like there should be probably a horizontal asymptote going off this way, but this drops down. I mean, it's a cubic, right? It's a cubic polynomial. It's going to go up on one side, down on the other. But at least through the stretch in through here, it's looking really good as compared to the slope field. Right? Now, perhaps you can see that what's going to happen, that each time you're going to just get one more term added on, and it's going to be the next bigger power of t divided by that factorial. In fact, this is the way it would look for the nth iteration of this. Now, some of you have probably had some sequences in series classes, something about Taylor polynomials, and you might actually start to recognize this as it looks a lot like e to the t, but it's not quite e to the t, because e to the t starts with a 1 plus all this stuff. So this is actually going to be e to the t minus 1, and in fact the solution to that differential equation, of course you can solve it with methods what we mentioned, is e to the e to the x minus 1. How about e to the t minus 1? This, of course, we've stated long ago, t equals x, right? I don't know why I have an x there. Anyway, let's take a look at this, this graph. So what I have is there's the initial one in purple, and then there's a red one in here. That's the second iteration. The black curve is the cubic, is the third iteration. I actually put the fourth one in there as well, that blue curve. But I also have, from all of that, I have the actual solution, y equals e to the t minus 1. Notice there is a horizontal asymptote at minus 1. And we can see that each time this curve is bending up closer and closer to that exponential. Now on this side, polynomials are never going to head off with a horizontal asymptote. But what's happening is that with each iteration, we're getting a polynomial that actually stretches further along this part. The next one would be up to fourth or fifth degree polynomial that would stretch down to here and then bend downward. And the sixth degree one would get out to here and go up. And that each time it moves a little bit further along as to where it converges. Sorry, it moves a little further along as to how close it is. The region that's the estimate is close to the actual answer. So anyway, we can see that sequence of polynomials converging to that exponential minus 1. All right. Now, let's do another example. This one is y prime equals t squared y minus t. This is not separable, and it is not, oh, it is first order linear. So I guess I could solve it. And actually, I tried to solve it, and I ended up with a really weird integral. We got to integrate like this negative t times e to the t cubed or something like that. I didn't want to do it. But the point is, even if you can't do it, I can get a pretty good idea of what's happening here. So here we go. Of course, the initial condition is y of 0 is 0. And here we go. So for the y, I plug that 0 in. So s squared times 0 minus s ds. Integrate from 0 to t. So that's just minus s squared over 2, which of course is then t squared over 2. And then you take that and plug it in for the y. So that gets multiplied by the s squared again. Then minus s. So I've got, what is this? S to the fourth over 2 minus s. So I integrate it to s to the fifth over 5 times 2 minus s squared over 2. Plug the t's in. I get that, right? So actually, I forgot to take a look up here. Let's look at the first iteration and how it fits with the slope field. It's going through the origin, and it looks like, yeah, this should be bending downward in both directions. So that upside down quadratic is pretty good approximation. But I can see right away that this should be bending back upwards over here, which it's not. And here it's bending downward, but maybe not fast enough. Yeah, definitely it's not going down fast enough to keep up with those. So, but at least close to 0, it's a good approximation. I'm sitting here in my home office, and my wife's donkey just ran by the window. It's like, I wonder if she knows he's out. So here's the next iteration. This is a 5th degree polynomial now, all right? So definitely bending downward there. And it's got that curve back upwards here. So this fits really nicely there. I think it fits better down along this side too. Definitely, I'm looking at how parallel the curve is to the slope fields, and it looks really good through this stretch here. So yeah, that's looking good. And then, we can keep going. Take this, plug it in here, and so then that's got to be multiplied by s squared, and then you have the minus s, and you integrate that whole thing. So I've got 3 terms now, and the s to the 5 times s squared becomes an s to the 7, so I end up, when you integrate it, at an s to the 8th. And apparently I didn't put the divided by 8 right here, but it is right there, so I'm going to ignore that typo because I got it right on this end. So Yeah, so now take a look at that. And this side was already looking good. This side's kind of snaking in through there. That's definitely looking good. Feels like it's going to need to head back uphill here. But this is headed down. I assume the next iteration will be going up a little better. Okay. On ones like this, it's like, do you have the ability to then see the pattern and write this down? Now, I don't necessarily expect students in an introductory differential equations class that have had a lot of experience with sequences and series. Now, we will later on in the quarter do quite a bit more with them. So the summation notation, you've done a little bit in Calc 2. You've probably never used this pi notation, which pi is like a product, where the sum notation is this. This is a product. So this is a product of things of the form 3i minus 1, where I goes from 1 to k, right? So with I equal to 1, 3 minus 1 is 2. That's that one. With I equals 2, you've got 6 minus 1 is 5, but you do it for, if k is 2, so when k is 1, you just get one thing on the denominator. When k is 2, you're going to do the sum from 1 to 2, so you're going to have a 2 and you're going to have a 5. When k is 3, you're going to have a 2, a 5, and an 8 here, right? So this is the product of things of the form 3i minus 1, where I goes from 1 to k, and k is running from 1 to n. And these exponents here are always of the form 3n minus 1, right? So for instance, I'm showing here 11. Actually, up to t to the 11th, but that's with 4 terms. So with n equals 4, this gives you 12 minus 1 is 11. Okay. One last example here. Sorry, right before I do the one last example, if you can write this is great. If not, I'm happy with something that looks like this, right? If you can see that there's a pattern being developed. I don't know what that function is. I don't recognize it as some function that I've dealt with before. Maybe if you've done more sequences and series, you do recognize this thing, but I don't. Anyway, one last example. Here we go. Y prime equals 2t. Now this one seems funny because there's not any y's here. I mean, couldn't you just say, y equals t squared? You probably could, right? That's not very hard to solve. But I wanted to show that Picard's method, in this case, actually gets it. It just nails it, right? You plug in y equals 0. Well, there's no y's here. There's no y's. So the 2t is just 2s, and you're integrating with respect to s from 0 to t, and you get t squared. And then you take that and you plug it in for y. There's no y's there. So you just have 2s ds, which integrates again to t squared. So Picard's method here keeps giving you the answer. It just says t squared, t squared, t squared, t squared. Like you should at some point say, I think the answer is t squared. Right? As soon as you get that point where the input is the same as the output, you've got the answer. So anyway, that's just kind of a silly example, but I thought I'd include it here. So anyway, there's some examples of using Picard's method to estimate solutions to first-order differential equations.